define the subfield or field in terms of evaluation homomorphism. Now first see the question. Let F be the subfield of field and define an evaluation homomorphism as phi of alpha 1, alpha 2, alpha 3 up to alpha n. आतापर्यंत आपण इव्हॅल्युएशन होमोमॉर्फिझमचे एक्झाम्पल कसे पाहिले, फाय ऑफ अल्फा आणि अल्फाची पर्टिक्युलर व्हॅल्यूज पाहिली. आता इथं फाय ऑफ अल्फा 1, अल्फा 2, अल्फा 3 अप टू अल्फा n as like n tuples. Okay, so it is defined over that field f of x1, x2, that is, it is polynomial ring having the coefficient in that domain to E and defined as for all alpha belongs to E. Next, second question, E is equals to capital F is equals to Q. Then we have to compute phi of alpha 1 value minus 3, phi of minus 3 comma 2. Okay, so and C question is define the concept of zero polynomial. Such a polynomial are in the variable of x1, x2, xn. That zero polynomial in terms of f of x1, x2 up to xn, it belongs to the polynomial ring capital F of bracket f of x1, x2 up to xn. Okay, so this is a question. Now we try to solve all the questions in that exercise. So all we know that what is the evaluation homomorphism for a field theory. If F is a field subfield of field capital E and alpha belongs to E with any element, then the mapping phi alpha of f of x to E defined as phi alpha of polynomial p of x, it is nothing but p of alpha. It is evaluation homomorphism. हे डेफिनेशन आपण शिकलो याच्या अगोदर. आपण ही डेफिनेशन काय केली, व्हेरीफाय केली, ही डेफिनेशन प्रूव्ह केली. ओके, सो आपल्याला इथे अप्लाय करायची डेफिनेशन कशावरती अप्लाय करायची, फाय ऑफ टपल्स अल्फा 1, अल्फा 2, अल्फा 3, अल्फा 4, अल्फा n. आणि हे इलेमेंट कशामधले, फील्डमधले इलेमेंट आहेत. ओके, सो इट इज अगेन ऑन द सेम डेफिनेशन ऑफ इव्हॅल्युएशन होमोमॉर्फिझम. मग इव्हॅल्युएशन होमोमॉर्फिझममध्ये आपण कसं डिफाईन करतो, फाय ऑफ अल्फा ऑफ पॉलिनॉमियल एफ ऑफ एक्स गोज टू एफ ऑफ अल्फा. मग इथं एफ ऑफ एक्सच्या ऐवजी काय, पॉलिनॉमियल इन टपल्स x1, x2, xn. मग तिकडे इव्हॅल्युएशन होमोमॉर्फिझममध्ये एक्स कशाने रिप्लेस होत होता, अल्फाने. मग इथे काय, x1 अल्फा 1ने रिप्लेस होईल, x2 अल्फा 2ने रिप्लेस होईल, x3 अल्फा 3ने रिप्लेस होईल आणि xn अल्फा nने रिप्लेस होईल. फर्स्ट क्वेश्चनचा आन्सर काय, वी हॅव टू डिफाइन दॅट इव्हॅल्युएशन होमोमॉर्फिझम. दॅट इव्हॅल्युएशन होमोमॉर्फिझम फाय ऑफ अल्फा 1, अल्फा 2 अप टू अल्फा n फ्रॉम capital F of we have to find the polynomial f of x1, x2, xn goes to x1 replaced by alpha 1, x2 replaced by alpha 2, f of alpha 1, alpha 2, alpha n. It is solution of first question. Now we solve the second question. That is, we given that what is value of alpha 1, alpha 2, alpha 3. We get alpha 1 and alpha 2, where value of alpha is minus 3, alpha 1 is minus 3, value of alpha 2 is 2. And what is polynomial, x1 square into x2 cube plus 3x1 raised to 4 into x2. मग काय करायचं, इव्हॅल्युएशन होमोमॉर्फिझम कसं डिफाईन करायचं, x1 replaced by alpha 1, x2 replaced by alpha 2. What is value of alpha 1? Alpha 1 ची value minus 3, alpha 2 ची value 2. Therefore x1 replaced by minus 3, x2 replaced by 2. Therefore from using the definition of evaluation homomorphism, we get answer minus 3 square into 2 cube plus 3 into minus 3 raised to 4 into 2. That is, answer is 72 plus 486. Answer is 558. Now to solve the C question. What is C question? We have to define the concept of zero polynomial. What is zero polynomial? That is a polynomial in terms of variable x1, x2, xn belongs to that the domain, that is the field of polynomial capital F of x1, x2, xn, and it is said to be zero. That is, alpha 1, alpha 2 up to alpha n belongs to capital E is said to be zero if f of x1, x2, xn belongs to capital F of x1, x2, xn that polynomial in x1, x2, xn must be 0. That is f of x1 comma x2 up to xn must be 0. Therefore, in that way we can solve that problem. So now next is important part, that is we have to prove and we have to define a division algorithm for a polynomial ring. Let f of x be the nth degree polynomial a0 plus a1x plus a2x square up to anx raised to n. G of x is mth degree polynomial b0 plus b1x up to bm x raised to n in f of x such that an is non-zero, bn is non-zero and m is strictly greater than 0. Then statement, there exists a unique q of x and r of x belongs to f of x such that f of x is equals to g of x into q of x plus remainder r of x. Then either r of x is 0 or degree of r of x is less than degree of g of x. So we have to define or we have to prove a division algorithm for a polynomial ring, as we define a division algorithm for a integers and so on. So on the same way we can define a division algorithm for a polynomial ring. We going towards the proof. Let s is equals to f of x minus g of x into s of x. S of x is field of polynomial elements. So s of x is 0 and s of x is 0 and f of x belongs to s, therefore s is non-empty. Why? Since s is a subfield of f of x. Now r of x is polynomial of minimal degree in s. Then what is r of x? R of x is in s, therefore r of x is in the form of f of x minus g of x into s of x. Therefore we define f of x, r of x is f of x minus g of x into q of x for some q of x belongs to f of x. So in that way we get f of x is g of x into q of x plus r of x. यास आपण define केले. For q and r are the two polynomials in f of x. Now claim is to prove that degree of r of x is strictly less than degree of g of x. So if r of x it is polynomial, so c0 plus c1x plus c2x square plus dot dot ct x raised to t, where ct is non-zero and t is strictly greater than 0. If t is greater than or equal to m, then r1 of x it is f of x minus g of x into q of x minus the coefficient divided by the non-zero factor, that is bm, ct upon bm into x raised to t minus m g of x. So we obtain that r1 of x it is r of x into that non-zero coefficient ct upon bm into x raised to t minus m into bm x raised to m plus bm minus 1 x raised to m minus 1 plus b1 of t plus b0. That is, the degree of polynomial is less than or equal to t minus 1, strictly less than degree of r of x, it is t. Now what is value of r1 of x? r1 of x it is f of x minus g of x into that fraction, that is q of x plus ct upon bm x raised to t minus m. Hence call it as q1 of x. r1 of x it is f of x minus g of x into q1 of x. Therefore r1 of x it belongs to s, since it is a polynomial of degree less than or equal to t minus 1, strictly less than t. This is contradiction, therefore r of x must belongs to that s, and our assumption that degree of r of t, what is degree of r of t? It is equals to t, it is greater than or equal to m, it is wrong. Hence r of x is 0 or degree of r of x is less than degree of g of x. Therefore for any two polynomials f of x and g of x belongs to f of x with degree of g of x is strictly greater than 0, strictly greater than 0, there exists a polynomial q of x and r of x in f of x such that f of x can be written as g of x into q of x plus r of x, called as equation number 2, with r of x is 0 or degree of r of x less than degree of g of x. Now for the uniqueness of r of x and q of x, let us q1 of x comma r1 of x belongs to f of x with another will satisfy f of x is bigger g of x into q1 of x plus r1 of x, called as equation number 2. Subtract equation number 3. Subtract equation 2 from equation 3. We get this side is same, so r of x minus r of x, it is f of x minus f of x, it is 0. 0 is equals to g of x into common q1 of x minus q of x plus r1 of x minus r of x. Now we get an equation r of x minus r1 of x, it is g of x into q1 of x minus q of x. That is g of x divides r of x minus r1 of x, where degree of r of x minus r1 of x less than degree of g of x by definition of divisibility. Therefore, what is that degree? That degree of r of x minus r1 of x, it is less than degree of g of x. Therefore, we must have r of x minus r1 of x, it is 0. That is r of x is equals to r1 of x, and hence we get the uniqueness. That is, if g of x into q1 of x minus q of x is 0, where degree of g of x greater than 0 and g of x must non-zero, we get q1 of x, it is q2, which proves the uniqueness of that division algorithm in f of x. Therefore, for two polynomial f and g in f of x, there is unique q of x, that is quotient, and r of x remainder, such that f of x is equals to g of x into q of x plus r of x, where r of x is either 0 or degree of r of x is less than degree of g of x. Therefore, this is same division algorithm for a field of polynomial or a field of capital F of x, that is polynomial having the coefficient in that field f. So we can apply that division algorithm for a corresponding field of polynomial. So in the next lecture we see the detailed examples of the division algorithm for a field of polynomial.